Yeah, so thanks for giving me an earlier slot. Yeah, so my name is Fidi, and I want to go back to the autonomous vehicle topics. So I want to point out some commonalities between state-of-the-art cars, so autonomous driving and spacecrafts. And maybe for an intro, so our company is trying to work in different areas and try to find core technologies which combine different areas to make the same core technology applicable in different kind of fields, be it in the NASA Orion or in the Ariane 6 rocket, Boeing 787. So these all kind of things have commonalities, and what you see up there is the Audi A8 or Volkswagen Group autonomous driving level 3 system. And I will now go a little bit into details. So here you see, so we're working on core networking and control technologies. And this control technologies, then we branch out into different kind of products that they can be used by different industries, be it in the highest safety and certification market, which is aerospace, or now in the industry 4.0, where it goes into industrial manufacturing or safety units for autonomous driving or for automotive, or be it snow groomers or different kind of other vehicles. So what we did for the Audi or for the Volkswagen Group, which now goes into production, 6 different types of cars, be it the Audi A8 or Porsche Cayenne. So we did a central driving assistance system, and we're providing here the software layer as well as the complete hardware design. And this is the first level 3 system, which is currently on the market. And I want to go a little bit into details. What does it mean? Yeah, so we are talking here about safety and fail operational. So this means we have different kind of functionalities, be it in town, in traffic congestion situations. Then we need to get to the acceptance of the customer. So the best autonomous driving system doesn't bring anything if the customer doesn't accept it. Then we have the legislation. So we need to get the proof that this system is allowed to be used on our streets. There is an extremely high cost factor. So if the costs are too expensive, this will never be used, and this will never get down into different kind of smaller cars in the future. We need a huge amount of computing performance for the whole data processing. I will talk about that a little bit later. And then we have a huge aspect concerning safety. So what kind of situations do we have? So we have here the safe operation in a normal scenario. Yeah, so this means I'm driving in a town, and I have to recognize all the different other cars, and I need to drive there carefully. However, I have some rare scenarios. Yeah, so I have, for example, here a deer on the street, and I have to brake, and I have to detect it. And this brings a lot of challenges. Then we have, let's say, standard things which you already have in the cars, like lane changing, recognition of cars in another lane, stopping and driving in this kind of scenarios. And then you have to also stop the car and avoid different kind of obstacles. So there's different fields, and there's different needs and different requirements, and how does it look like? So if we now look on a current car, so you have a lot of different kind of sensors, as you have seen before on the Audi A8. So you have here ultrasonic sensors, yeah, and these ultrasonic sensors or radar is used, for example, for autonomous parking, yeah, or for traffic jams. So when you are in a traffic jam, so this is what current state-of-the-art cars all have already. But the thing here is, so this is a quite simple scenario. Yeah, so I have here my sensors. I detect my very, very known environment, and I'm able to park autonomously by controlling the actuators. Yeah, but now I'm getting into different kind of other additional scenarios, like on the highway or in the park house. So I want to drive autonomous in a park house, and the car should go by itself, find a lot, and park there. And there you have different kind of other additional sensors, like LiDAR or more performant radar sensors. And you have to now also, next to the standard actuators, you also have to take care about the steering, and you have to have much more processing power already in the system. But this is some kind of a different kind of an application, because before you had a very known environment, now it's getting a little bit more tricky. And the worst thing is when you drive suburban, when you do not have a lot of signs, you do not have a lot of lanes on the streets, you are driving in the city. So you need to be aware of all the traffic around, and this can only be done by camera and by image processing. And this is where it gets really tricky, because there you need a lot of calculation, a lot of performance in the system itself. You have a lot of cameras which run with high HD TV or with HD or higher resolutions, and you need to do that fail operational and with an extreme high safety. So this is where it's getting really tricky. And when we look on the different kind of levels which are currently on the market, so you have here, so this is where standard cars are currently, yeah. So where the driver must continuously monitor the car. And then we have the level 3 system, where the driver needs no longer to continuously, let's say, maintain the car or check the car. And now it's moving into no driver necessary in special applications. Yeah, so it's moving into more autonomy, and it's really hard, because the processing power needed to let's say, crunch through all the numbers coming from the cameras is quite heavy. So how does it look like? So when we look on a level 4 system, so a level 4 system is really a system that can handle all situation automatically in a specified application case. Yeah. So this means if I'm on a motorway and so there is some problem, I need to be able to go on the side and stop. Or if I'm in this kind of scenario where I have some traffic congestions, then I need to avoid different kind of obstacles. The big problem in the automotive industry is now that we are moving from a level 2, level 3 system, so where the driver was still active and needed, into a level 4 system. And this means we are now going into from a fail stop into a fail operational environment. And now I have different kind of problems. So if I go here, for example, with 130 kilometers per hour, yeah, I'm going 360 meters in 10 seconds. Yeah. So this is a different scenario if I drive, I don't know, 30 miles on the motorway, yeah, and I exactly know how far I can get there in 10 seconds until the driver can take over. So here we are now really in a scenario where so the car really takes the autonomy and needs to decide by itself. So how do we get the link now to the aerospace or space world? So the planes are currently fly-by-wire, so they are failing operational or are fail operational. So this means in case of a fault, the system goes on and the system continues working. And the big problem now is if we take this approach and we go to the automotive industry, then we have the problem that we have a lot of redundancy. Yeah, so we have three times or let's say triple redundant architectures in current fly-by-wire applications. We have, for example, hardware diversity or diversity in software parts. So this means that's a big overhead that the automotive industry will not pay for. Yeah. So the question is how does it look like if we go into a level 4 system, and what do we need? Yeah. And we look into the ISO 26262. So this is the automotive standard for functional safety. Yeah. And there you see that there are different levels of functional safety. So up to level D. And the question is here, how does it look like? How is the goal to treat this kind of different faults in the future? So we are deciding here in systematic faults and random faults, yeah. And the systematic faults are then divided into software faults and hardware faults, yeah. And they say, okay, if you follow the process more and more strictly, you get up to this different kind of SIL levels, yeah. And the same for the hardware. So the hardware design with all the different kind of formal reviews and fault injection tests and so on. will bring you up to the dedicated levels. And then in addition, you have a lower fault probability for the ASIL. For example, you try to apply different kind of redundancy management, try to apply different kind of mechanisms like error correction or clock supervising or dual core lockstep. Yeah? So dual core lockstep is a typical way in automotive industry. So they design CPUs which are there 2 times and they check each other. And in case one of them fail, it fails silent. Yeah? And the question is now, what do we need to support this level 4 systems in the future? And here you see now, such a unit, like I shown before, is a partitioned, so it runs a partitioned operating system, a hypervisor on different CPUs. Yeah? And then you have the different kind of functionality. So you have safety applications, control applications, IT, media applications, security applications, and so on. So there are a lot of different kind of applications running on the same hardware. And the important thing now is that these different kind of applications are abstracted by the hardware and partitioned. And if this kind of applications are distributed, we need to partition the application on the whole distributed system. This means we need to have here interfaces which are partitioned. So I have dedicated address spaces, yeah, where I can communicate to them. And also the network needs to support this partitioning, which means time and space partitioning. Also over a distributed system. Before we talked about time and space partitioning on one hardware node, yeah, and now we are going from that into a distributed time and space partitioned environment. And how can we achieve that? We can achieve that by memory partitioning on the host itself, memory partitioning in the switches, so on the network, and time partitioning also on the network, to ensure that we exactly know what is going on. And the technology on which we have worked in the past years, called time-triggered Ethernet, is putting that into one protocol, which is the standard Ethernet part, which is running standard normal services for non-critical application, and can, in addition to that, run this time-triggered services. So this is the synchronous, fully partitioned service, and you see the time partitioning here on the network where you have different kind of frames, and these frames are scheduled. So they are partitioned in time on the network. And this is based on a fault-tolerant clock synchronization mechanism. So what is done there is, if you have this kind of redundant nodes on the network, you need to have one time on which you can trust to be able to have this fault tolerance. And this works so that you decide which nodes are used for this clock synchronization mechanism. And then these nodes send out frames, and these frames are then distributed into the network. And what you get here is then a global notion of time. And this global notion of time can now tolerate different kind of faults. So if one node is faulty, then the node will not affect the whole network, and you're operating on one synchronized clock. And this is the basis for this time partitioning and also for the space partitioning in the complete distributed system. And these are some kind of mechanisms you need to be able to work on such kind of systems like the level 4 system. When you now look to the message distribution, yeah, so based on this time synchronization, you can now do the network partitioning, because you exactly know on which time, at which time the message comes. It is then put it into a dedicated buffer, and then it's forwarded onto the network. And what you get here is you get a fully deterministic behavior from the send time to the receive time. You exactly know how long it takes. You get a constant latency and a very small jitter. And this then provides you the full determinism onto the network, and you exactly know at each time what is going on in your system. And we are working here with different kind of things. So if you're now running a packet over the network, so this is active redundancy. So you have two lanes, two-lane redundancy. If you run a packet over the network, you see how this works. And now we have to tolerate different kind of faults. So if, for example, one node starts babbling and wants to destroy, for example, the clock synchronization or the data, the switches are protecting the network from this kind of faults. So the switches will not allow to pass data which is faulty into the network so that the rest of the network is affected. And we call this kind of fault containment regions. So we can protect these faults. But what happens if the switch itself is faulty? Yeah? Then the switch would send out a different kind of malicious data into the network. And this we can protect by this kind of dual core lockstep mechanism. Yeah? So we have in the switch, we have a commander and a monitor, and they two perform the same function. And in case one of them is faulty, then the output will be cut and there will be no output anymore. Yeah? And with this kind of fault handling, it is possible to reduce the number of redundancy from 3 lanes to 2. And this brings a lot of cost advantage in this environment and helps to protect against different kind of faults. So we have done an integrated device, yeah, that has up to 25 Ethernet ports with the switch functionality, and it supports this kind of message passing. And now you see here this dual core lockstep mechanism. So there are 2 switch blocks on the same ASIC to reduce the power and to extend the integration density into on the same device. And the second one, so this COM1 approach, this dual core lockstep, so they have the same COM, so the module is the same. The clock is delayed between these 2 parts by 8.5 cycles to avoid common mode failures, and they share the same frame memory, but they have different configuration memories. So if there is a SEU or whatever in one of the configuration memories, the node will be fail silent. And this brings you the advantage then to have this fault containment region. And there is an internal comparison. So there is a comparator that compares the two switch blocks. And in case they have a disagreement, then the switch will shut down this message, so the message will not go out into the network. Where you have a big advantage because if you have 2 channels, you can decide either you get a packet or you get nothing because of this fail silent behavior. So how it is done again? It's done as in automotive. So you have separate silicon areas. So it's divided on the silicon area, and you have a clock observation of the clock to ensure that there are no faults driven by the clock. It has an end node, so that's the NIC, which provides you a complete IP UDP ARINC 653 stack in hardware, which is a big advantage because it offloads your CPU. And it also provides IP fragmentation and defragmentation up to 8 kilobytes of frames. And it provides you full diagnostics with different kind of interfaces like PCI, SPI, SpaceWire, UART, and so on. What is interesting is, so there is a full implementation of a in-hardware network stack, so an Ethernet network stack. And this can run raw MAC data up to ARINC 653 sampling and queuing ports. So this means you're communicating over UDP sampling and queuing ports. As I mentioned before, the partitioning, yeah. So this interface is configurable, and you can have here up to 8 partitions. So there are 8 different or separated address spaces on the controller itself. So you can connect that to in a multi-core CPU to different cores, or you can put that, or you can map that to different partitions in a partition operating system. And with that, you can achieve a full partitioning over the complete network. Then there is also a CPU, so there's a Leon 2 FT CPU in there with 125 megahertz, and this is running typically TFTP SNMP data, so it's behaving like a standard switch, not with the full functionality, but with the standard mechanisms with TFTP and SMP, so you can use it as a standard Ethernet switch. So to the conclusion, so what I wanted to show you is that there is high integration needed. So you need to integrate a lot of different functions into a unit to be able to support automotive applications. So to reduce the costs and you need to develop software which can be validated and reused between the different kind of units. So there is a trade-off between cost and complexity, because the complexity is growing, but you still need to handle the cost, which was a big issue at the development in our company, because we had around in the automotive application with the A8, we had 50 cars driving on the streets. We got a lot of different issues in during runtime, and at the beginning this was really a big challenge how to handle that. We had agile development with daily releases, and this was really hard to handle. We had more than 200 software engineers working on the program. And the whole system is going into fail operational. Yeah, so the autonomous driving is going from fail stop into fail operational environment. In the level 4 system, they need extremely high bandwidth. So the unit itself has a throughput of more than 12 gigabit of data, which is processed in real time. And the video data is processed by state-of-the-art graphic controllers. And how does it look in the aerospace market? So the recent developments are using automotive concepts, yeah, and they are also going in the direction of high integration. So as you have seen with our system on chip, we try to integrate a lot of different things and automotive functionality. The shift from the redundancy management to reduce the complexity and the software overhead. So we are moving. So with this kind of approach, we try to move parts which are done in software typically, like network stacks, like redundancy management or basic redundancy management. We try to move it into the network so that on the software level you have not that much complexity to be handled for this kind of things. Also for the clock synchronization. So this was the goal, so the goal is here to provide really solutions based on standard Ethernet for non-critical functions, as well as deterministic redundant Ethernet for high-end application, which really need to have this kind of redundancy concepts, and to try to really reduce the cost by using an approach which comes out of different industry and combine different industry or the core functionality of different industry, and then bring that out into automotive applications. Okay, thank you.
Thank you. Questions, or anybody has questions? Oh, Christian, you will be here for the rest of the day, or?
Yeah, for some hours.
For some time, some hours, okay. So if you have questions, feel free to go and meet with Christian outside. Yeah. He has a TTTech booth there.